All right, let's talk about efficiency. You know, it'd be great if we could find super efficient machines, if everything was 100% efficient. Unfortunately, we lose a lot of that efficiency, particularly in terms of heat. So we never get that. So we never get that ideal thing, you know. In real machines, we always lose some of it to heat, to friction. You know, friction usually changes into heat, and so on. So we're talking about efficiency. Here's my formula. Useful work output over total work input. Hey, if you can get 90, oops, that's not a 9. You know, if you can get 98 joules of work out of 100 joules you put in, hey, that's awesome. You got 98% efficiency. You know, technically, this should be kind of times 100 to give us a percent. Okay. All right, so here's what they're talking about. If you lose 2 joules to heat, you know, out of 100 you put in, you got 90% efficiency. They talk about pulleys. Pulley systems, not real efficient. You know, you might lose, out of that 100 joules, you might lose 40. So you may only have a 60% efficiency when it's all said and done. However, if you're still trying to get hay into the hay mow, it's a lot easier to do it from on the ground instead of trying to haul it up a ladder or something like that. So it's worthwhile in those cases. An inclined plane is another example of a machine. And if you push it up an inclined plane, you usually don't have to apply as much force to push something up than if you try to lift something straight up. You know, so here's this person pushing this block of ice up this inclined plane. Notice the inclined plane is 5 meters long. Here's the other guy. He says, hey, I'm just going to lift it. Now, he's applying more force. He's applying 5 times the force, but he only has to lift it 1 meter. She is applying 1/5 of that force, but she has to do it over 5 times. So my theoretical, in other words, if life is perfect, mechanical advantage is 5. Okay? Because we take the length of the plane divided by the height of the plane. So mechanical advantage, length of plane, height of plane. In this case, 5 over 1. So if you're trying to lift, let's say you have to lift a piano up a set of stairs, you know, the longer the plane, the longer you can make that plane, the less force you have in order to push that piano up. Okay? All right, and we talked about that already. So you lose a lot to friction, and we still got efficiency issues. You know, we're still going to get that same thing, the actual mechanical advantage over the theoretical, and it's going to be less than 1. Because you're not going to get 100% efficient. Here's the key, guys. Anytime that you do this and you say, hey, my mechanical advantage is 1.5, or if I did it in percents, 150%, you know right away that's wrong. You cannot get a mechanical advantage greater than 100% or greater than 1. Okay? It just doesn't happen. Now, here's another example of a machine. And actually, I don't know, they call this a complex machine. I would simply call this a screw. But what they're talking about, you know, what a screw is an inclined plane that goes around a cylinder. So really, it is a form of an inclined plane. I think they're calling this a complex machine because we also have this, which, you know, makes it a wheel and axle also. And so that's, you know, another simple machine. But, you know, all of these things, you know, multiply the force. So I can lift a car. Think about this, you know, the car jack. I can lift this heavy car just by simply turning this, and I really don't feel a lot, you know, it doesn't feel like a lot of force that I have to put into that. But I can lift the car so that I can change the tire when I do that. So this has a wheel and axle in it. The wheel and axle says that the handle is moved 500 times greater than the distance between the ridges. So my mechanical advantage might be 500. However, there is a ton of friction. I know in our Principles of Engineering class we've talked about, you know, the mechanical advantage of screws is very, very high. But the efficiency of screws is very, very low because you just don't get much out of it. Okay? I mean, so you use them because I don't have to put, you know, I need I need to multiply a lot of force, but I lose a lot to friction because of that. Oops, close you. Oh, that's not what I meant to do at all. Okay, that was weird. Okay, we're good. Go. If we're talking about an automobile, it's going to take chemical energy, change it into mechanical energy. There's a lot of energy in the bonds between molecules, so as it burns, we get a lot of energy released from that. But it's not very efficient. A typical gasoline engine, at best, 35% efficient. 65% of it we're losing. Think about this. If we would have a 100% efficient engine, it would not get hot. And think about how hot an engine gets when you put your hand on it after it's been running for a while. That wouldn't be happening if it was perfectly efficient. Well, we're never going to get that. You're always going to lose some to heat and things like that. And there's friction and other things, friction between the tires and the road and those kind of things. So you lose a lot of mechanical advantage, or a lot of efficiency, rather, in those examples. All right, so here's this child on a sled. His total weight's 500 newtons. Pulled up a 10-meter slope that elevates her a vertical distance of 1 meter. What's the theoretical mechanical advantage of the slope? All right, now, we don't really need to know that. All we need to know is, hey, 10 meters along the incline, 1 meter high, therefore 10 meters over 1 meter. Mechanical advantage is 10. Remember, mechanical advantage does not have a label because the labels cancel. So both meters, they cancel. So mechanical advantage is one of those weird things that doesn't have a label when you get it, or when you find it. All right, energy for life. There's more energy stored in the molecules in food than there is in the reaction products after the food is metabolized. This energy difference sustains life. In other words, we eat food to get energy. Okay, so every cell in your body, is like a machine. It needs energy, has to do things. In your body, you take carbon and oxygen together, and we form carbon dioxide. If you think about it, it's really, respiration is you take some hydrocarbon like glucose, C6H6O6, and you add oxygen. So you get carbon dioxide and water. That's your byproducts from that. Plants do just the opposite. They take carbon dioxide and water and form glucose and give off oxygen. Okay. So plants do photosynthesis, and they get their energy from the sunlight. So what they, if you think about it, almost all of our energy on the earth, almost all of it comes from the sun originally. So when we're talking about plants, they get that energy from sunlight. They change it into food, into sugar, through the process of photosynthesis. Okay, so like I said, almost all of our energy comes from the sun. We can do, now let's talk about energy source, energy things. So solar energy, we can take sunlight directly, change it into electricity. It is fairly expensive to do this. I mean, that's not a very cheap method, but you can certainly do it. You can also do it in indirect ways. They talk about how water evaporates and creates rain flow in rivers, generators, and so on. So there's, that's another way that solar energy gives us energy. Plus, I don't know if they talk about it later, but wind energy is also a form of solar energy. I think they do talk about it here in a little bit. So here's an example of some solar panels on a roof that could be used to power it. Yeah, here we go. Wind is also caused because, parts of the world get heated differently than others, and that creates wind. And wind, obviously, you've seen a lot of those wind turbines in Iowa, so we're used to seeing those, and they're very, very, they get a lot of electricity. They're very efficient for what we do. And obviously, wind energy is free. I mean, it doesn't take anything to get it. Of course, building the towers is pretty expensive, and they're pretty cool. I mean, they're huge. I mean, if you've ever been by those things, they're just absolutely huge. And those things, you know, they don't look like they're turning very fast, but if you were on the end of one of those windmills going around, I think you're going a couple 100 miles an hour. So, you know, they're moving pretty good clip when they're doing that. Fuel cells. This is kind of an interesting thing. There's more and more research into this, and we do some of this in our POE class. But fuel cells are they're really basically a battery. When you see something that says about a cell, they're talking about a battery. But we can take something like wind energy and power this battery, which is basically hydrogen and oxygen. And then when hydrogen and oxygen combine, we get energy from that. And the only byproduct is water, which is not a polluting thing at all. So it's a really nice form of energy that we can get. But you know, you're not creating energy, you're just storing energy. So you have to get the energy originally from somewhere and go into that. And you know, even a battery, any battery is like that. It got charged from somewhere, which is what gets me about electric cars. If they have a battery, that battery got charged. Where did that come from? It came from electricity, probably in your house. And that probably came from coal. You know, I think 70% of our electricity is produced through coal. You know, plus there's nuclear and so on. But I mean, that's where it originally comes from. So this fuel cell, you simply take the hydrogen and oxygen and put them back together and create electric current when you're doing that. These nuclear and geothermal, these are the ones that we could say maybe don't come from the sun, because these elements just have a certain amount of energy in them as they break up. They do that. And inside the Earth's interior, because of the mass of the Earth, there's a lot of nuclear power, radioactivity created. First, similar to the sun, not quite as big, obviously, but similar to that idea. And that has been with us all the time. And so, you know, you can tap into that. You know, a lot of times we have geothermal heat. You know, this school now uses geothermal heat, where we've just run pipes down into the ground to get, you know, heat from the ground. Now, around here, we're not drilling way down to get really hot. But what we are able to do is get, you know, down. If you drill down a ways, you find that I think the temperature always stays right around 55 degrees. And so, you know, when it's 20 degrees out, we can still get this water at 55. And so then we only have to heat it up another 15 degrees to get it to normal temperature, versus otherwise you got to take air, you know, that's 20 degrees and heat it up to 70. All right, so geothermal, we talked about that.